Hey everyone, welcome to a journey that's going to take us from the farthest reaches of space to the innermost workings of the human mind. So buckle up, get ready to expand your mind, and let's embark on this incredible adventure together.
So, what exactly is the philosophy of science? Well, imagine you're a detective arriving at a crime scene. The philosophy of science is like that detective's toolkit for understanding how scientific inquiry itself works. It's about asking the big questions. What makes something scientific? How do we distinguish between science and pseudoscience? Science isn't just about collecting facts and figures, it's a way of thinking, a method for investigating the world around us. Philosophy provides the framework for critically examining the nature of scientific knowledge itself. Science gives us the what, the facts, the data, the observations. Philosophy of science grapples with the how and the why, how we acquire scientific knowledge and why we should trust it.
Let's dive into one of the most fundamental questions in the philosophy of science, the demarcation problem. This issue has puzzled thinkers for centuries and remains a hot topic of debate even today. How do we draw a clear line between genuine science and pseudoscience? This question is crucial because it affects how we understand and interact with the world around us. This isn't just an academic exercise, it has real-world consequences. Mislabeling pseudoscience as science can lead to misguided policies and wasted resources.
One of the key criteria that philosophers of science have proposed is falsifiability. This concept was popularized by the philosopher Karl Popper. For a theory to be considered scientific, it must be possible to conceive of an observation or an experiment that could potentially prove it wrong. This means that the theory must make predictions that can be tested. For example, Einstein's theory of general relativity made specific predictions about how light should bend around massive objects like stars. These predictions were later confirmed through observation. This ability to be tested against evidence from the real world is a hallmark of genuine science. It allows theories to be validated or refuted based on empirical data. Pseudoscience, on the other hand, often relies on vague or untestable claims. These claims cannot be empirically tested, making them immune to falsification. By applying critical thinking and demanding evidence-based reasoning, we can better navigate the world of knowledge and make more informed decisions. This approach helps us distinguish between what is scientifically valid and what is not.
Let's delve deeper into Karl Popper's concept of falsifiability. Popper argued that true scientific theories are those that can be falsified, meaning they make specific predictions that can be tested and potentially proven wrong. He believed that the goal of science shouldn't be to seek confirmation of our existing beliefs, but rather to rigorously challenge them and see if they hold up to scrutiny. Imagine you have a hypothesis that all swans are white. According to Popper, a better approach would be to actively search for black swans. If you find even a single black swan, your hypothesis is falsified, and you've learned something new. If your hypothesis withstands repeated attempts to falsify it, it becomes more robust and reliable. While Popper emphasized the importance of falsifiability, the ability to test and potentially disprove a theory, Thomas Kuhn offered a different perspective on how scientific progress unfolds, challenging the traditional views. Kuhn argued that science doesn't always proceed in a linear, cumulative fashion, where each discovery builds neatly on the last. Instead, scientific progress is marked by periods of relative stability, which he called normal science, punctuated by revolutionary upheavals known as paradigm shifts, where the entire framework of understanding changes. During periods of normal science, scientists work within an established framework, or paradigm, conducting experiments and making observations that fit within this accepted model. This paradigm provides the guiding principles, the accepted theories, and the methods that shape how scientists approach their research, essentially defining what is considered legitimate science. But sometimes, anomalies arise, pieces that don't quite fit, observations that challenge the prevailing paradigm and cannot be easily explained away. As these anomalies accumulate, they can create a sense of crisis within the scientific community, leading to intense scrutiny and debate. A paradigm shift represents a fundamental change in the way scientists view the world, leading to new theories and methods that redefine the field. Let's dive into the Duhem-Quine Thesis, which argues that it's impossible to test a scientific hypothesis in isolation. This idea challenges the notion that we can pinpoint a single cause for an observed effect in scientific experiments. Imagine you're testing the hypothesis that a particular fertilizer increases plant growth. You might think that by simply adding the fertilizer, you can directly measure its impact. You conduct an experiment, adding the fertilizer to one group of plants and using a control group without the fertilizer. This setup seems straightforward, but the reality is more complex. At the end of the experiment, you observe that the plants treated with the fertilizer have indeed grown taller. This result appears to support your hypothesis. Can you conclusively say that the fertilizer alone caused the increased growth? The Duhem-Quine Thesis suggests that you can't be entirely sure. There are always other variables to consider. There might be other factors at play that you haven't accounted for, differences in soil composition, water availability, or even subtle variations in sunlight exposure. These factors can all influence the outcome. Scientific hypotheses are always tested within a web of background assumptions. These assumptions are interconnected and can affect the results of any experiment. This suggests that scientific knowledge is always provisional. Our understanding evolves as we uncover new information and refine our assumptions. Let's explore a fundamental debate within the philosophy of science: scientific realism versus anti-realism. This debate centers around whether scientific theories provide us with true descriptions of the world as it really is, or whether they're merely useful tools for making predictions and explaining observations. Scientific realists believe that science aims to uncover the underlying reality of the universe. They argue that successful scientific theories accurately represent the way things are, even if we can't directly observe them. Anti-realists, on the other hand, are more cautious about making claims about the true nature of reality. They might argue that scientific theories are just models or representations that help us make sense of the world. This debate has important implications for how we interpret scientific progress. Let's delve into the underdetermination of theories by evidence. This idea suggests that for any given set of observations or experimental data, there might be multiple, equally plausible scientific theories that could explain them. Imagine you're a detective investigating a crime. You gather evidence from the crime scene, interview witnesses, and piece together a narrative of what you believe happened. But what if there's another possible explanation, another suspect, or a different sequence of events that could also account for the evidence? In science, the same principle applies. Multiple theories might be compatible with the available data, making it difficult to definitively prove which theory is the correct one.
Let's turn our attention to the crucial role of models and simulations in scientific practice. In many scientific disciplines, it's impossible or impractical to study real-world phenomena directly. That's where models and simulations come in. Think of a model as a simplified representation of a more complex system. A simulation takes that model and uses it to explore how the system might behave over time or under different conditions. For example, climate scientists use sophisticated computer models to simulate the Earth's climate system. Models and simulations are powerful tools for scientific inquiry because they allow us to explore complex systems, make predictions, and test hypotheses. However, it's important to remember that models are simplifications of reality.
As we explore the frontiers of scientific knowledge, it's essential to consider the ethical implications of our work. Science doesn't exist in a vacuum. It's conducted by people within societies, and its applications can have profound impacts on our lives and the world around us. Data integrity and research misconduct. How do we ensure the accuracy, reliability, and objectivity of scientific data? Informed consent and human subjects research. When conducting research involving human participants, how do we obtain informed consent? Animal welfare in research. What ethical considerations should guide the use of animals in scientific research? Emerging technologies and societal impact. As new technologies advance, what are the potential ethical implications?
As we stand at the precipice of new scientific discoveries and technological advancements, the philosophy of science is more relevant than ever. One exciting area of exploration lies in the intersection of science, technology, and society. As artificial intelligence and machine learning become increasingly sophisticated, they challenge our notions of knowledge, objectivity, and even consciousness. Philosophers of science are grappling with questions like, how do we ensure that these technologies are developed and used ethically? Another frontier lies in the realm of complex systems. philosophers of science are exploring new ways of thinking about emergence, complexity, and the interconnectedness of systems.
Well, there you have it, folks. A glimpse into the fascinating world of the philosophy of science. Remember, the quest for knowledge is an ongoing journey, and the philosophy of science provides us with the tools and perspectives we need to navigate the complexities of the universe and our place within it. So keep questioning, keep exploring, and never stop wondering about the world around you. And don't forget to subscribe to our channel for more mind-expanding explorations into the realms of philosophy, science, and beyond. Until next time, keep those cosmic questions coming.